Hi, this is our third set of notes, part 3 from Chapter 2, Phase Diagrams of Pure Fluids. The focus of this set of notes will be on cubic equations of state, and at the very end we'll briefly discuss the Racket equation. So just like the last set of notes on corresponding states theory and virial equation, this set of notes will be more of a discussional type of presentation. Right? So similar to a lecture you might normally see in your classroom, we will discuss cubic equations of state. In class, we will solve problems together, and then I will also post sample videos and sample MATLAB code to help facilitate the use of cubic equations of state for solving problems. Okay. All right, so as mentioned, this is our third set of notes from Chapter 2, Phase Diagrams of Pure Fluids, and we'll focus on cubic equations of state and briefly discuss the Racket equation at the end. So just like the last set of notes, we're going to begin by looking at our ZP graph, where we actually ended off on our very first set of notes, and then our quote from John Prausnitz. Do the best work in thermodynamics that you possibly can and enjoy it thoroughly, but don't lose sight of the goal. Thermodynamics comes second, first comes chemical engineering. Right? So our goal is to develop useful expressions so we can solve real, practical problems. Okay. So what we've done so far and where we're going is in the last set of notes we talked about three-parameter corresponding states theory. Okay, and so I mentioned these are often called generalized correlation or Lee-Kessler tables. Those are just the folks that tabulated values. But in general, these three-parameter corresponding states theories are limited to simple and normal molecules, and they're only suitable for modeling a single phase. They can't be used to model, say, vapor-liquid coexistence. We had the virial equation of state, which is our only theoretical expression, and it involves an infinite sum. It's generally truncated to one or two terms, and this limits it to essentially just modeling gas phases. And in this chapter, we'll introduce cubic equations of state. Cubic equations of state are applicable to liquid and vapor phases, and forms are applicable to modeling not just the simple nonpolar molecules, but polar molecules as well. Right? And the development of cubic equations of state and equations of state in general is still an active field of research and still developing and changing today. So characteristics of a cubic equation of state is I would call them semi-theoretical. Okay? And so what we mean by that is that their physical form starts with some physical argument or theoretical argument in mind, but then at the end of the day, they're ultimately engineered or tailored for accurate calculations. So the first cubic equation of state we'll talk about is the van der Waals equation of state, which originated in van der Waals' dissertation defense back in 1873, and this is the first of 100 such equations. Okay? We'll talk about two equations of state that followed van der Waals, namely Suave-Ruther-Kwong and Peng-Robinson in this chapter as well. So before we discuss van der Waals and SRK and Peng-Robinson, the one thing I would like to mention is, from my experience as a student, it can often be a little overwhelming, right? In your textbook, you learn about these different cubic equations of state, and then that leads to the question of, I'm working for some industry someday, I need to model a given process, which cubic equation of state should I use, right? Sometimes this material is often presented that you should just know, okay? So what I want to remind you of is that you shouldn't necessarily know. When you go to work for an industry, right, you'll start out getting paid some money, and then the hope is the longer you work there, the more and more you get paid, right? And why that is because with experience comes the ability to, say, choose which cubic equation of state is best for a given piece of process equipment in your company. Okay? So when it comes to how do you choose cubic equations of state, a lot of that comes with experience. Okay? And if you don't have massive amounts of experience, where I would point you is there's a valuable textbook out there called The Property of Gases and Liquids by Poling, Prausnitz, and O'Connell. So chapter 4 focuses on equations of state. And so essentially what they've done is they've taken all of the popular equations of state and they evaluate their performance for modeling a wide range of processes. Right? And so here's just a snippet from the introduction where they make such recommendations. And one of the projects we'll work on in class is an exercise similar to this where we'll evaluate the three cubic equations of state that we'll talk about in this class for modeling vapor-liquid coexistence and we'll compare to tabulated reference data from NIST. Okay, but before we proceed, as we talk about different equations of states and models altogether in this class, just keep in mind that how you actually choose a model, you'll ultimately develop that ability to choose with experience. Okay, it's not something I would expect you to necessarily have by the time you leave this class. So van der Waals equation of state. Okay, so we said van der Waals equation of state we could call a semi-theoretical model. And so the general idea is, what is an ideal gas? Well, an ideal gas is a system in which our molecules don't interact and they don't take up space. Okay, so an ideal gas, molecules don't interact, they don't take up space, and they're described by the ideal gas equation of state. So here I have it written as P is equal to RT over V, where I remind you again that V is the molar volume. Okay, so van der Waals started essentially with the ideal gas equation of state, and he said, well, that's great, but molecules take up space and they interact. And so just this general physical notion led to this modified equation. So the van der Waals equation of state takes the form of P is equal to RT divided by V minus B minus A over V squared. Okay, so this takes into account this assumption that molecules take up space and they interact. Okay, so they take up space, so that's accounted for in this term. So remember, our ideal gas equation of state is P is equal to RT over V. So what we've done here is we've rewritten that essentially as P is equal to RT divided by V minus B. The general idea here is that the volume of interest is the volume available to a molecule, right? And so if I'm a molecule and I take up space, that space that I occupy isn't accessible to me and really should be excluded from our calculation, right? And so essentially you could think of this as being like a equation of state in which rather than using the volume, the actual volume, we use the free volume. So we remove the excluded volume occupied by a molecule. Now the second term, minus A over V squared, okay, this accounts for the fact that molecules interact. Okay, so it's negative. Okay, so as we saw back in chapter 1, these attractive dispersion interactions are going to be favorable. They're going to be negative. Okay, and so it's written as minus A over V squared. Where this V squared comes in is, if you remember, London showed that these dispersion interactions are going to scale as 1 over r to the 6. So if I'm trying to develop an equation for actual practical calculations, okay, knowing the average interaction distance of my molecule in my system isn't going to be something I readily know or have, but we expect that should scale with 1 over v squared. Right? So if I think about my molecules sitting on a cubic lattice, we had such an exercise back in chapter 1, then the interaction distance is going to be proportional to volume to the 1/3 power. Okay, and so based on that, then 1 over v squared should be proportional to 1 over r to the 6. Okay, and so that's where this term comes in. This is meant to account for dispersion interactions. Okay. Cool. So we have a 2-parameter model. So in the limit that we have an ideal gas. So an ideal gas is obtained at constant temperature in the limit that V goes to infinity or pressure goes to 0. And so at constant T, in the limit that, where am I looking at? So Z is PV over RT. So I rewrite this as V over V minus B minus A over RTV. In the limit that V goes to infinity, then this is going to go to, Z is going to go to 1. Okay, cool. All right, so van der Waals equation of state. So why is it called the cubic equation of state? So as we'll see in 2 slides, is we can take our equation, which is naturally written to be explicit in P, and we can rearrange it so it's a cubic equation in Z. So why we like solving for Z as compared to P is Z is generally bound between 0 and 1. Okay, and we'll look at a couple of pictures on the next slide. But in general, especially near coexistence, Z is bound between 0 and 1. Okay, there are some exceptions in extreme cases that we'll look at. Where on the other hand, if I think about volume or pressure, the range of volume or pressure can be quite large. Okay. The other advantage that Z will offer as we start to look at vapor-liquid coexistence is there'll be cases where I can actually get two real roots, right? I can simultaneously model a liquid and vapor, okay? So again, I know those z's are going to be essentially between 0 and 1, and then it's pretty easy to identify which one's liquid and which one's vapor by the vapor being closest to 1, liquid being closer to 0. Yeah, volume, I could compare, say the larger one would be a vapor and the smaller one would be a liquid, but again, that range or what those values are ahead of time could be rather large and could be kind of hard then to know if the results are reasonable or not. Okay, so if you look at a couple of pictures of our compressibility graphs to get an idea of the range of Z, so what's given here on the left is the Z versus P diagram that we've been looking at. Okay, and so as I've mentioned, this is our coexistence curve. Okay, so if I am looking at states near coexistence, okay, then my Z values are going to be between 0 and 1. Okay, so when we multiply vapor or model vapor-liquid coexistence, my Z's will be between 0 and 1. Okay, and so that's nice and convenient. And the values of Z closest to 1 are going to correspond to a liquid phase, and the Z's closest to 0 will correspond to a liquid. Okay, so if I am above my saturation curve over here, right? This is our superheated liquid or superheated vapor. My apologies, my superheated vapor region. And so if I look at my isotherms here, in general, if I'm in the superheated vapor region, okay, I'm going to be a root closer to 1 relative to 0. If I'm in the subcooled liquid region, in general, I'm going to be closer to 0, right? I'm going to be smaller, right? At the very least, if I'm on a given isotherm, okay, and if I'm in the superheated vapor region, well, if I'm in the superheated vapor region, my root's going to be larger than if I'm in the subcooled liquid region. Okay, but there are some exceptions. And so what I did is I used a cubic equation of state to essentially try and construct a similar diagram, only I've looked at some more extreme conditions. And so this is Z versus reduced pressure. So not pressure, reduced pressure, so I could try and make it universal. And my isotherms are in reduced temperature units. Okay, so if I look at this pinkish one here, this is at a reduced pressure temperature of 0.8, so it's below my critical point. So this would correspond to vapor. So my vapor side over here. Okay, then it's flat as I move across my coexistence curve, and then here's my isotherm in the liquid region here. Okay, and so what's useful to look at, or what I'm trying to point out, is here in this diagram. Okay, when I look at pressures, the diagram gets cut off at pressures not too greater than my critical pressure. Okay, here, remember this is in reduced pressure units. So this dotted line here corresponds to my critical pressure. This dotted line here corresponds to my critical temperature. And so what I'm looking at here then is reduced pressures all the way up to 10. So up to 10 times larger than my critical pressure. And so if I look at even this isotherm then, so this is at a reduced temperature of 0.8. Okay, so near coexistence, we said we're bound between 0 and 1. But then if I continue to increase the pressure, my compressibility actually continues to increase and can actually take on values greater than 1. Okay. This solid black line is at a reduced temperature of 0.6. Okay, so essentially it's way down here on the small scale. Okay, so if I'm at a low reduced temperature and I continue to increase the pressure, eventually I end up getting compressibilities greater than 1. Okay, but I would consider these more of extreme conditions. For the conditions of this class and for most processes that you'll probably look at in your future, you can think of this phase diagram. And if I think about my saturation curve, my Z's are going to be bound between 0 and 1. If I'm in superheated, they're going to be closer to 1. If I'm subcooled liquid, they're going to be closer to 0. Okay, these are at extreme conditions and very unlikely that you'll encounter them. Okay, if you do encounter them, you'll probably be aware that they're extreme conditions, and you might need to go back and look at your notes. Okay. So van der Waals equation of state. Okay, so Z, my compressibility, is defined as being PV over RT. So what I've done here is I've taken our expression for P from my van der Waals equation of state and multiplied it by V over RT. Right, so we get the following expression. Then to eliminate V, we plug in that V is equal to ZRT over P. Okay. So in doing so, right, we get this. And then what's done here is I've introduced two terms of b prime and a prime. Okay, where a prime is defined as ap over rt squared, b prime is bp over rt. Okay, so remember a and the van der Waals equation state is our attractive term. That's going to correspond to our interaction energy. B is corresponding to our excluded volume term. Okay, so I have a times p over rt squared and b times p over rt. Okay, and then finally, with some elbow grease rearranging, I can cast this expression in the following form. Okay, and so when I express in the following form, it takes the form of an expression which is cubic in z. Okay, so I have z cubed, z squared, z. Then this could be thought of as multiplied by term z to the 0. Okay, so in rearranging, I get an expression that's cubic in z. Okay, and the significance of an expression that's cubic in z is that tells me for a given, say, temperature and pressure, I can get more than one real value of z. So what that's going to tell us is that for a given temperature and pressure, if I'm at coexistence, I can simultaneously model both my liquid and vapor phase. Right? Cool. Okay. It's a cubic equation of z. There's lots of techniques out there to find roots. If I'm near coexistence, then I expect my z's to be bound between 0 and 1. Okay. So scenarios that we can have. Okay. So it's a cubic equation, so we can have from 1 to 3 real roots. Okay. So it's capable of describing phase transitions. So for given temperature and pressure, it's possible to have more than two real z's. And so that would correspond to simultaneously describing both my liquid and vapor phase. So if you were to get 3 real roots, you would throw out the middle one, right? Because we know that we would want the smallest one, which would correspond to my liquid. My largest one would correspond to my vapor. And the one in between would technically be metastable. If I'm not on my coexistence curve, so if I'm in superheated vapor or compressed liquid, then in order to identify your z, well, a couple of different situations could exist. One would be I solve my cubic equation of state and I find that there's only one real z. If that's the case, well, then there's no decision that has to be made. That is your z, right? And hopefully that corresponds to what you would expect in superheated vapor or compressed liquid. The other scenario would be if, say, I'm in the superheated vapor region, but I'm not too far away from my saturation curve. Okay, so at my saturation curve, you will definitely have 2 real roots. If I move slightly off my saturation curve, you will more than likely still obtain 2 real roots. So in those situations, then you need to identify which root you want to choose. So if you know that you're in the superheated vapor region, then you choose the one closest to 1. If you know you're in the compressed liquid region, then you choose the one closest to 0. Okay. So again, on my saturation curve, you'll get 2. Okay. As I move slightly off my saturation curve, you will still get 2. Okay. It's only once you move well beyond my saturation curve or reasonably well beyond my saturation curve that you'll begin to get just 1 real root, at which point you'll need to know what phase you're in terms of identifying which one to use. Okay. So this just has some tips about how you might go about solving for those z's, and we'll look at some examples in class. I will also share with you some MATLAB code that you can use to find roots of z, and there's also an Excel sheet I'll share with you from colleague Richard Elliott for you to play around with. All right, so van der Waals equation of state. So if you recall back in Chapter 2, well, at the beginning of Chapter 2, so our first set of notes, when we were looking at our PV phase diagram, I mentioned that this critical isotherm is fairly special, right? And what makes my critical isotherm special is that it goes through an inflection point. Well, so its first derivative is 0 at my critical point, and it goes through an inflection point at my critical point. Okay, so remember this point is going to correspond to critical pressure, and then this is my critical isotherm, right? An isotherm at my critical temperature. So where my critical isotherm hits my critical point, its first derivative is 0, and it goes through an inflection point. Okay, and where this will be useful is if we take van der Waals equation of state, this gives us essentially 2 constraint equations that expression should conform to. Okay. So if we take that and we apply it to the van der Waals equation of state, so here I have my expression explicit in P, right, and I'm differentiating with a constant T, right? So looking at my isotherm, I can compute my first derivative and second derivative. And then I can force it so that the first derivative and the second derivative both have to be 0 at my critical temperature. And if I do that, I find that A and B can be defined in terms of just critical constants. Okay? And so now the significance of this is if you were to go back a couple of slides, okay, when we had our polynomial expression for z, we had these parameters big A and big B, where big A was little a times p over rt squared, big B was little b times p over rt. Okay, so what this tells me is that A and B aren't just adjustable parameters, but instead, if I know my critical parameters, which are typically tabulated, that's sufficient to be able to calculate A and B, which can then be used to calculate any PVTA behavior that I could possibly want for that fluid. And even in Chapter 5, we'll see how we can calculate other things. Okay, so knowing just critical properties would allow me to calculate essentially everything I could possibly want to know about a given fluid. Okay, so cool. So one shortcoming essentially of van der Waals is if we plug these constants back in and solve, we find that it predicts a universal critical compressibility of 3/8. And this isn't the case. It's typically smaller than 3/8. So while this is convenient and is a beautiful result, we know that it's not going to be very accurate, or its accuracy is going to be limited, and that it doesn't, predicts this universal behavior which isn't correct. Okay, but that's okay. Okay, so here's our final form of our van der Waals equation of state. So this one's explicit in P. Here's our cubic equation that we had solved for. There's big A prime and big B prime, which I just mentioned. Where now, though, A and B aren't adjustable parameters, but I can calculate them solely from my critical temperature and pressure. All right, and so this is beautiful. So the van der Waals equation of state is essentially two-parameter corresponding states theory. If I know my critical temperature and pressure, along with the temperature and pressure of interest, that's sufficient for me to calculate Z and then ultimately molar volume of my fluid. Okay, that's amazing, right? And we said that it's capable of modeling vapor-liquid coexistence, and so we'll see later on how we can actually go from just knowing a critical temperature and pressure to then go and map out an estimate of vapor-liquid coexistence, and then eventually calculate a whole slew of thermodynamic properties. All right, but we said that this equation was limited, right? It predicted a critical compressibility of 3/8, right? And in theory, it's a two-parameter corresponding states theory. So we had talked about two-parameter corresponding states theory in Chapter 2, okay? And so, what would Pitzer do? So when a two-parameter corresponding states theory is insufficient, add a third, okay? And if you recall, the parameter that Pitzer added was the eccentric factor, omega, okay? And so that's what's essentially evolved since then. So we had the van der Waals equation of state, which is a two-parameter corresponding states theory, okay? The next equation we'll talk about is the Soave-Redlich-Kwong SRK equation of state, okay? So remember, van der Waals was P is equal to RT over V minus B minus A over V. So what you'll notice in the Soave-Redlich-Kwong equation of state is he adds this additional term, okay? So van der Waals was RT over V minus B minus A over V squared, right? So he adds this, or he modifies, this term in my attractive term, where if I were to expand this out, this is, V squared plus BV. So essentially what SRK is added is this plus BV term in the denominator of my attracted term, right? Where B, again, is going to account for some excluded volume effects of my molecule. So we could take this expression, cast it in the form of a cubic equation, okay? Same expressions for big A and big B exist relating to little a and little b, okay? Only now, in terms of calculating A, B, and omega, we end up needing a third expression, and our third expression is going to be the definition of eccentric factor, which we bring in, okay? So now we have a three-parameter corresponding states theory where little a, my attractive term, is also dependent on, here it's written as big omega, where big omega is a quadratic equation with respect to little omega, my eccentric factor, okay? So this is the small modification that SRK made. With this now becomes a 3-parameter corresponding states theory, where we also introduced a dependence on eccentric factor. And what do you know? SRK performs much better than van der Waals by the introduction of this third term. The other one we'll talk about in the book is in the class is the Peng-Robinson equation of state. So again, van der Waals is P is RT over V minus B minus A over V squared. And now we've added this term plus 2BV minus B squared. Right? So you could factor out a B if you wanted to, but that's the term. We could also take this and express it as a cubic equation. Big A and big B are the same. And again, we have 3-parameter corresponding states theory to get little a, little b, where my attractive term now A is also dependent on big omega, where big omega is a quadratic equation of my eccentric factor. Okay, so my attractive term is now also a function of my eccentric factor. Okay, but again, keep in mind, if you were to look in the back of your book in the appendices, okay, critical temperature, critical pressure, critical volume, and eccentric factor are tabulated for a wide range of fluids. And part of that is partially motivated by cubic equations of state. You have to appreciate the beauty of these things. Okay, so if I am a process engineer and there is 100 different fluids that I could possibly encounter or work with in my plant, okay, and I have to model all these, one option would be to go and measure vapor-liquid coexistence data for all 100 species. Okay, that's option one. Option two of what these cubic equations of state allow you to do is, rather than measure vapor-liquid coexistence, they tell me if I just have an estimate of eccentric factor, critical temperature, and critical pressure, that I can use that with my cubic equations of state to predict everything else, right? And so that's amazing. That's pretty awesome. Okay, and so the note here is, this modification term changes a little bit, and then all the prefactors change a little bit. Okay, and so these cubic equations of state are engineered or optimized for different applications. Peng and Robinson were up at University of Alberta. Their equation of state was optimized for petroleum industry. Okay, so but that's another case where, again, how do you choose a cubic equation of state? Experience. Right? It's a matter of, if you ever have to use a cubic equation of state to model a piece of process equipment, then you do your homework and you learn from the older people in your company in terms of historically what's worked, what doesn't work, and maybe why. Okay, so cubic equation of state. So get the idea. Many others exist. Even modifications of van der Waals, SRK, and Peng-Robinson exist, such as these volume translated equations of state, which are generally recommended. But again, how do I choose? Experience, or I would advise you to have a look at Pulling, Pronzitz, and O'Connell, Chapter 4, where they've taken all these equations of state, evaluate them for a wide range of systems, and then make recommendations. Okay, so that wraps up cubic equations of state. So the last thing that comes up in the text is the Racket equation, so general correlation for liquids. And so it takes the form that VL sat, so my molar volume of my liquid at saturation, is equal to VC times ZC. So critical volume, critical compressibility raised to 1 minus TR raised to the 2/7 power. Okay. And so the simple equation is generally accurate to 1 or 2%. So if I just need to estimate molar volume of my liquid, this equation in general is very accurate if you have access to VC and ZC. Okay. And then, if you think back to our PV phase diagram when we first started, as long as I'm at low temperatures, so in general, dV, dP at constant T is essentially 0. As my temperature increases, that changes a little bit. But if I'm at low temperatures, essentially well removed from the critical point, so this equation, although it's was developed to correlate saturated liquid volumes, if I'm well removed from my critical point, so if I'm at low reduced temperatures, you can use this to approximate the molar volume of your liquid. So if I had to estimate a molar volume of liquid water at 25 degrees C, all right, use of the Racket equation would probably give you a very good estimate. Okay. And that's the end of our Part 3 notes. let's continue this discussion in class, and we'll solve some problems in class as well.